Hi, it's repair time. If you follow me on EEVblog 2, and you should, you would have noticed that I had a problem with one of my oyster lights in my kitchen, and well, it was sending alien signals or something. It looks like an alien spaceship, and it was flashing a weird code. So anyway, I've ripped it out. I've brought it into the lab here, and I've hooked it up, and that's what it's doing. Let me turn the lights off. So I've just got it hooked up to a LED string, which I ripped out of an old LCD dumpster TV. It's come in very handy. I've used it for quite a few videos, actually. The LEDs have got like 5 volts drop per LED. They're actually quite high. And yeah, they're in string configuration. I use them for all sorts of things. I've got 2 strings of those. Yeah. Does anyone know their Morse code? What's that flash in? Yeah, it's hiccuping. So anyway, that is obviously hiccuping, as they call it. That's one of the names for the fault. I don't know if you call it something else, but yeah, in the industry, it's often called hiccuping, and the mains power supply is hiccuping. It just can't start up. It's trying to start up the mains side of it, but the main switching side, but it just can't do it. So it keeps retrying, and no, it just comes a gutser every time. So anyway, let's take this thing apart and see if we can find the culprit. All right, we're at the Teardown microscope, but I've got something a bit new for you today. I've now integrated my NI National Instruments Virtual Bench scope. It's just sitting right down here next to me, and I've got my probes. I can have my oscilloscope probes. I can have power supply, function generator, logic analyzer, digital I/O, everything integrated into my video capture system, which not only I can record with, but I can also stream as well. So you'll see in my straight ahead camera, I've also got my Teardown microscope. Here it is right under me, and there will be a B cam, but it's not hooked up at the moment. And also there's my National Instruments screen. But one of the cool things I can do now is I've set it up so that I can now overlay, ta-da, this. I can overlay the multimeter here. So here's the multimeter winner, and all the power supplies as well, and there's some digital I/O in there as well, and I can stream that, and yeah, that's really cool, huh? So anyway, let's get to it. Let's have a look at this. Okay, so let's have a look at the driver here. It's a Lucci thing, model number for those playing along at home. It's a dimmable jobby, and it's a 2-watt LED. That's individual LED. It's actually up to 20 or 22 watts output. So it's actually rated for up to 80 degrees. But yeah, anyway, let's have a look at what's failed here. Here's the output section. Now, I wouldn't expect... There's no bulges in those caps, of course. First thing you look for is bulges in the caps. But, oh, I forgot to tell you that this actually comes with a heatsink over here, and it's just screwed in there. And I've taken that out because we want to see some stuff under there. It's a couple of extra caps. And anytime you see caps near or under heatsinks like this, yeah, you want to be suspicious of those puppies. So anyway, I've taken that off. So yeah, it's just a plastic package. So that's just like they didn't even bother with the heatsink compound. So they just bit how you do it. They just slapped it on there, but, you know, better than nothing, I guess. These are shy caps on the output. Now, it's not going to be the output, A, because those caps look in good nick, and B, there's multiple ones in parallel. So, like, you know, I wouldn't be concerned with that, and that's not going to cause the power supply to hiccup. Now, is this a secondary regulator? Yes, it is. This is a secondary regulator. Okay, because here's the primary secondary split. So this is all the secondary side. This is the mains input over here, like this. And so these are my initial thoughts. I'm pretty sure it's not going to be this secondary side. I mean, you can go in there. Obviously, you do a visual on the caps, but these have got the vents on the top. I can't see any bulges whatsoever. They'd be in parallel if you actually follow the money on there. Yeah, parallel, and another one there. Is it? Don't know if there's 4 in parallel or whatnot. No, there's another one that's not in parallel. So we've got 3 in parallel. So when you've got 3 caps in parallel like that, it's not going to be the output caps. And really, the output driver side of things, you're generally not going to see like a hiccup, as we call it. That's usually a primary side thing where this converter can't start up. So yeah, I would not be looking at the secondary side, I'd be looking at the primary side. Now, they've actually rubbed the number off this chip, so we can't see what this is. Maybe I could get a knife on there and try and scrape it off, but I think that they've actually scraped the number off that chip. Anyway, you want to give a visual on here, and one of the first things I notice is that there's discoloration around there, that resistor in there. Is that my imagination, or is that a bit discolored too? That looks a bit how you're doing, doesn't it? So we'll get in there and measure that, and you can see that on the bottom as well. Look, you can see the fiberglass, and like you start seeing like the weave in the fiberglass pattern, right? You don't see that anywhere else. That means this has been heated up to buggery, and yeah, it's just the fiberglass is not you know, your high temperature, high quality stuff, so it's just start to decolor, and yeah, it's not looking good. Also, you can see the same thing effect happening over here as well. So that's under what's that under? That's these big resistors over here. These are just input resistors, are they? Yep. So yeah, they're just input limiting surge resistors, whatever. Anyway, yeah, there's no major caps on the input, even though this is a full wave bridge rectifier. They just don't need a massive amount of capacitance on the input. Now, of course, as I said, these caps are under and near the heat sinks here. So you would suspect these puppies, right? 50 volts. And they would be to do with the startup as well. I don't know what that... What's that in there? Is that a ST25C? Is that just an external switching transistor? I have to look that one up. ST25C, it's a BJT, it's an NPN BJT. Yeah, it's just a jelly, looks like it's just a jelly bean BJT. No worries. And we've got a bunch of diodes in here as well. You could go in and you could measure those as a matter of course, but I'm really quite concerned. That resistor there is heated up a lot, and it's right next to the caps as well, let alone the heat from the heatsink. But that resistor, that's obviously gotten hot because it's just, yeah. So anyway, let's turn on our multimeter, shall we? And let's have a probe in there. What value is that? Brown, black, something or other. Brown, black, burnt. Brown, black, burnt is the value of that resistor. Now, when resistors get hot like this, obviously they're not going to be in the kilo ohms or the hundreds of kilo ohms, because Ohm's law, you'd need like thousands of volts before you do anything, you know, actually heat them up. So this is going to be a low value resistor. And was that a gold band on there, like, you know, like a silver or something like this one over here? Anyway, so that's supposed to be a low value. So let's measure that, shall we? 287K. No, there's nope. Houston, we've had a problem. The resistor is, that is Gonski. That is Gonski. I don't need to measure anything else. I mean, I could. I mean, I could whack, I could go diode mode, and I could go start checking my diodes and stuff, but you want to fix anything you come across. 0.56, no, 0.67. I think we're good on the diodes. You just check diodes because they're easy, you know, and you can generally check them in circuit. 0.7, you know, no wuckers. So yeah, I can't see visually anything else, really. I mean, these suckers, they like it's discolored. I mean, it's discolored, and it's 270K. Nah, that doesn't add up. That does not add up. So we've come a gutser there, and we could have found a culprit. Is it that easy? Is it one resistor? Oh, let's hope so. Makes for a boring video, but anyway. Oh, wow. That other joint, I haven't even desoldered that. And that other joint's Gonski. That's the other thing that I should have looked for on my visual, was joints. And let's actually go down here. Oh, hang on. There's a pin sticking out. No, that can't be it. And oh yeah, that one. Look, yeah. Yeah, there you go. It's is that just a that's just a oh, that's just a transformer leg. Okay, that's right. Yeah, there you go. This sucker has heated up so much that it's just delaminated. The copper's just delaminated from that. Wow. Yeah, that's Gonski. Need to tongue at the right angle there. Jeez, there we go. Got that characteristic Bernie smell, that Ernie Bernie smell. And yeah, that is one sick. Oh, look at that. That's cracked a buggery. Wow. Wow. That sucker's had a harsh life. Look at that. So that's, well, no, I thought that was brown, black something. It's red. What is it? Red, brown? Something? I don't know. That's terrible, Muriel. Wow. Yeah, that is completely gone. No wonder. Wonder if we can just, like, is it just going to fall apart? I wonder if we just grab that with 2 pliers, is that going to come apart? Oh, no. It's still strong as a mallee bull. But, yep. It is completely cracked. It's Gonski. And that, of course, is probably open. The 270K was measuring in circuit. And, yep, it's Gonski. So, it could just be the resistor. That just heated up so much that it eventually went open. And I can guarantee it'll do exactly the same thing now if we power this up, because that resistor's missing. It was open before. It's still open. So yeah, maybe that's it. Maybe did they have the wrong resistor value? So it's got to be like a piss poor design, because like you wouldn't design it so that resistor heated up so much that it failed like that. And it's not like like an ambient thing because it's inside the oyster light. I mean, that doesn't help, right? The fact that it's got no airflow in those sealed oyster lights upside down on the roof. But wow, you know, that's just that's a harsh life. It's not good. Don't know. It could have been brown. It could have been black. That's just faded. It could be gold. That's just faded. That third band. It does matter. It matters a lot because that's the that's the multiplier. So I'd be tempted to go with gold, maybe. So we're talking like 1 ohm. Silver would be, like it does look red on the screen here, but when I look at it with my eyes under my proper color lights here, it looks brown. So I think it's brown black, and it's just I know it does look red on camera, but when I look at it straight, it's actually it's more brown. So anyway, that's what I'd expect. Yeah, I'd expect like in the order of like ohmskis. So where is it in circuit here? There it is there. That's one of the transformer taps. These are the transformer taps along here. I don't really want to reverse engineer this. So, no, that's a large value resistor in there. Yeah, so I'd say that's just a current shunt resistor. Is it? Don't know. I'd have to look up a typical primary side switcher for that, because this obviously it's not doing the regulation on the primary side, it's doing the regulation on the secondary side here. That's the only reason why you'd have the SO8 controller there, which I think they've rubbed the numbers off that puppy as well. I think the conformal coding doesn't help because like you can still see the diode marking on the diode bridge over here. Yeah, I've tried to scrape that away, and it's just there's nothing under there. But yeah, I don't know. Like just throw in a couple of ohms or something and see if it gets it back on track. So I'll actually leave this one sticking up a bit. Why not? That's not going to touch the heatsink. Just leave it up there like that, rather than have it right down on the board. That gives it some extra heat sinking due to the legs. Whoops, that pad's lifted, didn't go through. That's a bit cleaner. Hopefully she'll go through now. That's the problem with lifted pads. Really rather annoying to try and get these back through. I think I got it. Yep, sweet. So I'll just leave that flapping around in the breeze up there. And Bob's your uncle. So here's our main primary switch-in transistor over here. You can see that goes over to the coil there. And that's our resistor in there now. So it seems like that is not in the way of, it goes under there, it goes over to here, which is then that small little TO92 transistor we saw before. So I'm not seeing how that's part of the main line. So I'm not seeing how that resistor is in series with the main switching transistor there. So that shouldn't be a problem even if we make that too low. I don't know. But yeah, if it was in series, then obviously the value is going to matter. But yeah, because it's in there, I don't know, there's this extra switch in tranny in here. That's like, it's probably doing some like power factor correction as well, something like that. So it's obviously doing something different. So maybe, as I said, like it could be some other sense resistor or something like that. But it obviously heats up. So it's important to get that value right. It's going to be critical, and well, I don't know, cross your fingers and hope I've got the value right. But anyway, yeah, let's just power it up, whatever. All right, let's give it a bell, see if we get anything. Whoa! Magic smoke released. Holy crap. I guess that's the wrong value. Whoa. Wah, 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 wah. Yep, I would say that wasn't gold, that band. That's what happens when you underestimate the value. The actual resistor's fine. But look at the input. It was obviously drawing like probably an order of magnitude more current. And those input resistors from the mains, nothing else seems fried, which is really interesting. But those, wow, look at those input resistors there. They are just, they're burnt. They are horrid. That is unbelievable. Yeah, I've completely kamikatze. I don't think I'm going to bother to fix this now. I'll just probably upload this as a hilarious what not to do. Yeah, I got a bad, my spidey sense gave me a bad feeling just before I was about to switch it on. I thought, oh no, I'm going to kamikatze. I think I should have gone up in value rather than down. Yeah, that was dumb, wasn't it? Actually, I presume that's an input fuse there. That just goes to show how poorly that's rated. That input, I'm going to cut that off because like that should have popped before all of those just absolutely cooked. Yeah, I think they've rated that wrong. Oh, no, so much for that. I thought that that'd be a little axial fuse in there. But it's not. It's just a resistor. Anyway, oh boy, those puppies cooked. Sorry if you got that fan noise in the background. That's my filter going berserk here, trying to get rid of the wretched smell from this sucker. Yeah, well, that's embarrassing. That's double facepalm worthy. Yeah, please leave it in the comments down below. I'm an absolute dill. But I thought I had the right value, but then I knew that. I should have actually at least attempted to reverse engineer this, see what was going on there, see exactly where the resistor was. The lower value was always going to be a concern, but I thought it was gold in there. But it's, yeah, that multiplier band is going to kamikatze. Obviously, yeah, I was off by at least an order of magnitude. But it seemed reasonable at the time, because if you have a look here, here's the resistor here, and it goes under there, and it goes to this small TO92 MPN transistor that we looked at. So it's not like, you know, that's going to be carrying amps or anything. So it's not the emitter resistor in the main switching transistor, which will be in series with the transformer over here. So it's not that. It's somewhere else in here doing something. But obviously, given the size of that resistor and the fact that it's heating up, yeah, it was obviously doing something more important and dissipating a fair bit of power. So with hindsight, yeah, that was just a dumb 1.8 ohms. Was a dumb choice. Yeah, it just didn't put the thinking cap on enough. Oh. Alright, I've decided to do a basic reverse engineering here. It's not complete, so please excuse the crudity of the model. Didn't have time to build it to scale or to paint it. So I'm going to work out where I goofed up. My first goof was not remembering that this is a dimmable LED controller, which means that it has to start up at low voltages, which means it's going to need some sort of low voltage startup, you know, just in case the dimmer, when you turn it on, is like set to like a low voltage, like, you know, 50 volts, you know, something like that, or whatever it is. Anyway, yeah, we've got 240 in, you know, there's some filtering and other stuff over here, and including the resistors that burnt the hell out. And then we've got a diode bridge rectifier, and then we've just got a main small filter cap, which is here. And then here is our mystery resistor right here, and it looks like, yeah, we've got a basic Zener circuit here with a emitter follower transistor here. That's a little TO92 jobby in there, and that just powers the 8-pin chip. I still don't know what that chip is. Look up dimmable flyback LED controller or something like that, and there's 10 million of them, but it's more likely to be one of like the lesser known like Asian variants or something like that. Anyway, yeah, and then of course the DC, the main couple hundred volts DC powers the transformer over here, just like I suspected, with of course the main switch-in MOSFET here, and then the other 1 watt resistor down in here, which I knew was the series resistor for that, and obviously they're tapping that off somewhere else. I didn't bother, you know, going into details around the controller chip. But then you've got a tap coming off the primary of the transformer here, which goes via a diode, and that goes into basically bypassing the 180k. And the other resistor up here, the 180k 1 watt jobby, that's the other 1 watt resistor up here, which wasn't cooked at all. So you wouldn't expect that 180k to be dissipating much at all, because it's basically in parallel with the coil over here, and which of course can be low impedance to then drive directly into our main Zener dropper down here. Obviously this is going to be a Zener. I don't know the voltage, but I did. There it is, tiny little jobby down there. It's a sad looking thing, but it has had the snot blown out of it. It's measuring like 3 ohms, so yeah, that's no good at all. So that's not one of the original faults. That would have happened in my goof up, and we can see how it's blowing here. This I totally goofed up. I thought it was some other, you know, current sense resistor or something dumb like that. I just, you know, it didn't have my brain engaged. And of course, if you did some basic reverse engineering, you would have seen that this was a Zener dropper, basically. So this needs to be in the order of tens of Ks. So that resistor value probably is either 10k or 20k. So that third band, which I thought was gold, was actually, I think it was orange. So yeah, so I think this was originally a 20k resistor, and here I am putting in a 1.8 ohm. So I was only out by 4 orders of magnitude. Oh! So we can see now how it snotted itself. Yeah, we've got our high voltage DC here, basically going straight through the coil like this, and then straight across through the diode. I'm surprised like the diode survived, and straight through basically a short circuit, which then snotted the Zener down here, so it failed short circuit. So if either of those failed open, then yeah, we wouldn't have had the magic smoke escape. It just would have went pop, and pop goes the weasel, and yeah, it would have been fine. We wouldn't have burnt the input protection resistors over here. They wouldn't have turned completely black and charred like that. So yeah, we just, it looks like I haven't measured this other diode. That could be shorted as well, likely. So yeah, it just, boom, went straight down like that. So this should have been, you know, 10 or 20k, something like that. And yeah, complete goofarama. I chose poorly.
He chose poorly.
and what that Zener voltage there would have been, you know, it's like in the order of maybe 20s, you know, the tens of volts, 20 volt. I mean, there's, you know, a 50 volt rated cap. Both of these caps are 50 volt rated here. And I won't go into details about, you know, how all this works. Doesn't really matter. If anyone does know, can, you know, guess based on the basic, at least some of the pinout I've got here, exactly what chip that is, please leave it in the comments down below. And if you do want me to do a complete reverse engineering, well, if we got that chip, we probably shouldn't have to. They've probably got an example circuit in there. It's probably almost identical to the example application circuit. They usually are. Very few differences usually. But anyway, if you want me to do a full reverse engineering, then, you know, leave it in the comments down below. But we just needed to know where I goofed. And that's what it is. It looks like it was a Zener dropper circuit. Oh. So yeah, that was embarrassing, wasn't it? But anyway, I hope you found that valuable. My goof is your gain, I guess, in terms of, yeah, just, you know, like a couple of more minutes. If I didn't rush this thing, a couple of more minutes just figuring out exactly what that resistor was doing would have prevented this. Obviously, if I knew it was a Zener dropper like this, there's no way I would have made that like, you know, ohms. I would have made it tens of ohms, something like that. And I would have probably guessed, you know, it's not going to be like in the hundreds of K region. It's going to be in the tens of K region if you do your Zener, you know, dropper calculation and stuff like that, assuming like, you know, a milliamp or two draw in here and the minimum Zener current. You can work out, you know, a basic, you know, ballpark resistor value, and it's going to be in the tens of K region, something like that. So yeah, I definitely wouldn't have made that mistake if I simply went and spent a little bit more time doing the reverse engineering. So let that be a lesson to you. Anyway, I hope you found that valuable. If you did, please give it a big thumbs up. As always, discuss down below. Catch you next time.